Hi, everybody. As you can probably tell, I am not actually Theo Jacobson, but I am giving his talk today because if you were here yesterday, you already saw him give a very nice talk when he stepped in at the last minute for Alexi, who was out sick. So thanks for bearing with us as we shuffle around which speaker is giving which talk at this conference. So I'm going to be talking about universal deformations, and this is based on a paper that Alexi, Theo, and myself put out last year. So the bulk of the talk is going to be about confinement in 2 dimensions. And so the main thing we want to think about is we start with some generic 2D gauge theory, maybe with matter, maybe without matter. And the main question that we want to ask is, does it confine or not? So we know that this is a sharp question if there is a one-form symmetry, in which case the question becomes, how is that symmetry realized? Is the one-form symmetry spontaneously broken or not? And right away, we run into some tension because we have the Coleman-Merman-Wagner theorem, which in its familiar form tells us about no spontaneous symmetry breaking in quantum mechanics. We can upgrade that to 2 dimensions, and that would tell us that there's no discrete one-form spontaneous symmetry breaking in 2D. So this is a pretty strong statement. You know, if we think of this really as a theorem, it's a very strong statement. And the implication of no discrete one-form spontaneous symmetry breaking would be that we cannot get deconfinement. However, we definitely have examples where we do in fact get deconfinement. So here's some counterexamples studied, in the 90s, and again more recently, for example, massless Schwinger models, and also with some assumptions, massless 2D adjoint QCD, and other QCD-like theories. So as usual, we're going to be spending a lot of time thinking about Wilson loops when we discuss confinement. And so specifically in 2D, Wilson loops are going to be special because they're going to separate space-time into 2 disjoint regions, the inside of the loop and the outside of the loop. Now, if there's a one-form symmetry that acts on Wilson loops, there's going to be a distinct sector for each one-form charge. And we call these sectors universes. And these different universes are separated by infinite tension domain walls. So we can think of these as the probe Wilson loops, not dynamical ones, the probes that we put into the theory, and that will separate these sectors like the inside and the outside of the Wilson loop. And the important thing is because these domain walls have infinite tension, there's not going to be any mixing between these sectors, even in finite volume. So in particular, that tells us that the full path integral decomposes. We can write the partition function as the sum of the partition functions from the individual universes. So for example, if we have SUN adjoint QCD, there's a ZN one-form symmetry, and the different universes are going to be labeled by the anality of the different representations of the Wilson loop. So there's a direct relationship between the Wilson loops, these universes, and what it tells us about confinement. So in particular, we can think about the energy densities of the different universes and what that tells us about what's going to happen to the Wilson loops. So if we think about this first picture on the left, suppose there's a higher energy density inside the Wilson loop than in the universe outside the Wilson loop. That is going to lead to an area law, and we're going to pay this area law cost to try to make the Wilson loop bigger. We can also think about that sort of as a time slice of that Wilson loop, which would be the quark picture on the bottom left-hand side. So somehow the energy density between the 2 quarks is bigger than outside, and we get confinement. On the other hand, if the energy densities in the universes inside and outside the Wilson loop are the same, we're going to just have a perimeter law, and so we get deconfinement. Now, we also know that there's a lot to be gained from considering symmetries from this more modern perspective of topological operators. So in particular, for us, we're interested in one-form symmetries in 2D, which means that the topological operators that we care about are going to be local topological operators, or LTOs. So without loss of generality, we'll just consider discrete ZN symmetries here. And the important relation is going to be the linking relationships between the LTOs and the charged operators, which are the Wilson loops. And in particular, if we look at the action that the LTOs have on the Wilson loops, basically they will tell us the one-form charge of the Wilson loop as we execute this action of moving the topological operator across the Wilson loop. And from this property, we can determine that the expectation values of these UK local topological operators are going to label the different universes. So depending on what universe we evaluate this expectation value in, it's going to give us a different phase that labels those universes. Now, because these operators are topological, in particular, this is telling us that the endpoint functions are also topological, so they don't depend on the insertion points of these operators. Specifically, the 2-point functions are going to be topological, and from that we can deduce that these UK operators have scaling dimension 0, which is very important because it tells us that they are maximally relevant deformations. So that's what we're going to do. We're going to take advantage of these LTOs, construct deformations out of them. Because they're maximally relevant, something interesting should happen. And we pick some energy scale lambda to perform this deformation at. And so this brings us to the reason why these deformations are called universal in the first place. So on the one hand, they are very generic. All you need is a 2D gauge theory with a one-form symmetry. And right away, because of the very nice topological properties of these operators, you can exactly calculate the effects of this deformation. So in that sense, they're very universal because they apply to all these theories and it's just exact and you can just do it. They also are called universal because the net effect is that they shift the relative vacuum energy densities of the different universes. And as we know from before, those vacuum energy densities are precisely the thing that's going to tell us whether the Wilson loops have an area law or a Perberger law, and hence tell us about confinement. So let's go through a simple example in the charge n Schwinger model. So this is 2D QED U1 gauge theory with a charge n Dirac fermion. So this has a Zn one-form symmetry generated by these UK topological operators. And we can think about them in a couple ways. For example, as Glukov-Witten disorder operators from a more abstract perspective, or also we can think about them very concretely if we switch to the bosonized form of the theory, in which case we can actually write an expression for the topological operators explicitly in terms of the fields. And this is very nice for doing concrete calculations. So that is actually what we do. And it's been known for a long time that the massless Schwinger model is deconfined. And in more modern language, we would say that that's because there's a mixed anomaly between the Zn 0 form chiral symmetry and the Zn 1 form symmetry. So if we turn on a mass, that explicitly breaks the chiral symmetry and we get confinement. So that is all the case without the deformation, just the usual story. Now we turn on this deformation, which is built out of these LTOs that are the generators of the one-form symmetry. Because there's the mixed anomaly, these UK operators are going to be charged under the chiral symmetry. So adding them to the action, again, explicitly breaks the chiral symmetry. But it turns out it does not actually generate a fermion mass. And so you can see this picture in the lower right-hand corner sort of tells the story about what's going to happen. So if we start out with no mass and no deformation at the origin, that's the usual story. We're in a deconfined phase. And then continuously connected to that in parameter space, there's always some balance of the mass and the deformation that you can tune to each other that will basically cancel out the effect on the energy densities and bring us back to a deconfined phase. So in this way, we can control whether we're in a confined phase or deconfined phase. So just in pictures, going through that in a little more detail. So this is specifically for the charge 2 Schwinger model. So we have two different universes, and those are represented by these two curves of effective potentials for each universe. And they're as a function of the compact scalar in the bosonized variables. So starting on the far left, we have no mass, no deformation. It's the usual story. We have deconfinement. The two minima are at the same value, or the two minima are equal, and so we have a degeneracy and hence deconfinement. Then on the bottom, if you turn the mass on, you lift out the degeneracy, you get confinement. And furthermore, when you turn on the mass, it changes the shapes of these two potentials. And so that tells us something about the spectrum of the particle excitations of the theory. And this can be contrasted to the top picture, where we have set the bare fermion mass to 0, turned on a deformation. Again, we lift the degeneracy, we get confinement. But in this case, it does not change the shape of the potentials. They still remain the same. And so that tells us that we're not generating a mass, and the spectrum of the particle excitations are going to be the same. Then, as you wish, you can change M and the deformation in such a way that they balance out in terms of their effect on the energy densities. We can make the universes degenerate again. And so even with a mass turned on in the Schwinger model, we can still reach deconfinement. So all of that was a very explicit example of how this works when we turn on these deformations in the UV of some theory. But we can also think about what's the picture with these deformations when we think about flowing to some IR EFT. And this perspective was suggested to us recently by Mitat, Neuzil, Mendel, Wen. So thanks to them. So first of all, we can start out with some 2D gauge theory, or maybe something that's even microscopically a higher dimensional gauge theory, but that's going to ultimately flow to some 2D EFT in the IR. And we want to think about what's the state of that long distance 2D EFT with a one-form symmetry. What's the generic expectation? Do we think it's generically going to confine? Is it generically going to deconfine? What is going to happen? So we want to know what happens to those Wilson loops. So let's just consider one of those situations and see what happens. So suppose we end up with a ZN one-form symmetry that is spontaneously broken. So the simplest possible example of this would be some BF theory, which is a TQFT with n degenerate universes. Since we have degenerate universes, again, we have deconfinement. And if we think about it a little bit more, why that happens, it's because there's a zero form symmetry that shifts this phi that has a mixed anomaly with the one form symmetry. So again, that's kind of the explanation for why we have deconfinement in this case. However, this is special because unlike in higher dimensions, the symmetry is not robust. And it's precisely because of these universal deformations that are relevant and can be generated in general, barring some other symmetry that might be preventing them from happening. So generically, because these are relevant deformations, we would expect them to be generated in the EFT, and that is going to drive us away from this deconfined endpoint, and we're going to end up with this BF term plus some other contribution from these universal deformations. So we're going to get confinement with some relation to the, with string tension related to the scale of the deformation. And some of the details about how the microscopic mechanisms for these generations of these deformations is worked out in an upcoming paper by Mitat and Mendel. So I'll just point you to keep an eye out for that if you're interested in the details here. So to summarize, we see that confinement is the generic outcome when we're considering what happens to these 2D gauge theories as we flow to the IR. So we start out with some 2D gauge theory with the one-form symmetry. Because we have these relevant universal deformations, in general, those are going to be generated. We're going to end up in a confined phase. Of course, we can fine tune to try to avoid that, or we can also enforce an exact zero form symmetry with a mixed anomaly to try to end up on one of these deconfined phases. But the general outcome is that we're going to have these deformations generated and end up with confinement. So we can interpret this as the modification of the Coleman-Merman-Wagner theorem, because even though it is possible to end up with deconfinement, the generic outcome is that we don't have spontaneous symmetry breaking for these one-form symmetries, and we get confinement. That concludes my talk. Thank you very much.
So if n is large enough, then I guess you have several parameters to play around with, right? So you can also get weird phases where charge 1 is confined, but charge 2 is not, and then or vice versa.
Yes, yeah. If you have if you have lots of different minima, you can potentially introduce multiple deformations if you want to try to get all of them to be deconfined. But yeah, in general, you'll just get some of them. Yeah.
So characterizing the phase picture is more than just this confined, deconfined. Everything can also work.
Sure. Yeah.
In your graph, you plotted somehow the theta equal pi vacuum was always higher, but can you get theta equal pi lower?
Yeah, in general, yes, you can move these relative to each other in any direction.
So that is okay.
Yeah.
More questions? If not, let's thank Maria again.